Okay, so this is a similar problem to what we discussed in class. So let me read the statement for you. So we have a disk that is spinning counterclockwise. So the angular acceleration velocity is positive. So it's a 2 kilogram disk. It has a diameter of 30 centimeters or a radius of 0.15 meters. The initial angular velocity is 300 rpm, and the friction coefficient between the brake and the disc is 0.1. And we want this thing to stop. The time that we want this thing to stop is 3 seconds. So the question is, what is the force P, the normal force P that we need to apply to the brake so the friction here would stop this disc in 3 seconds if it is spinning at 300 rpm. So let's do this problem in a few steps. So first let's calculate the torque. And I'm going to just use letters, and then at the end I'll put the numbers. Let's calculate the torque. So the torque, so if this is the disk, right? So this is the center of rotation here, and this is your radius r. Then the torque here, right? This thing is spinning this way. So the torque here is the friction force times r. And that friction force is mu times the normal, which in this case is P. So that's the friction force. So therefore the torque applied by that friction force is produced by that friction force is mu times P times R. So that's it. That's the first part of the problem. So now that we have the torque, let's apply Newton's second law of rotation. So that says that the torque is equal to the moment of inertia times alpha. So the moment of inertia of a disk, and you have this in your tables that you're going to get with your equation sheet, is 1/2 mr squared. So then all I need to do now is write that alpha is equal to the torque divided by I. So the torque we calculated before is the friction coefficient times the normal force P times R divided by 1/2 m r squared. And then I can cancel the r's, and then I get that this is mu P, and then I'm going to get a 2 on top, and then I get mr. So on my mu, this is mu. I'm gonna just change all the mu's to mu k, just to make sure they don't get confused with the mass. So I have now the angular acceleration written in terms of P. So the next thing is to apply kinematics. So kinematics. And so we're going to use this equation. The final angular velocity is equal to the initial angular velocity plus the acceleration times delta t. And so for this thing to stop, we want the final angular velocity to be 0. So therefore, I can write that alpha then, this is going to stop when alpha is equal to the initial angular velocity divided by delta t. So, and then the alpha we calculated before, alpha is 2 mu k times P divided by mr, right? So that is alpha. That has to be equal to omega 0 times delta t divided by delta t, sorry. So now I have an equation that I can solve for P. So I'm going to solve this for P, and this is omega 0 mr divided by 2 mu kp times delta t. So now I can solve for P. All I need to do is put the numbers. So there's one more detail though. Omega 0 is in RPMs. So I need to change that to radians per second. So 300 RPMs to radians per second. For that, I would have to multiplied by 2 pi and divide by 60 seconds in a minute, right? So one revolution is 2 pi and there's 60 seconds in a minute. And so if I did that, I'm going to get that this is 31.4. So omega 0 is 31.4 radians per second. So then now I can solve for P. P is equal to 31.4 radians per second times 2 kilograms times the radius, which is 0.15 meters. All this divided by 2 times the friction coefficient. And I put P twice, so here there is a little mistake here. That P should not be there, so then I get P times delta T, right? So then this is 3 seconds. And so I can put all those numbers in my calculator, and I already did that. And if you do that, you're going to get that this is 15.5 newtons. So the force that you need to apply to stop this disc is a force P that is normal to the disc in the direction of the brake, and it has to have a magnitude of 15.5 newtons.